Okay, all right. So, you've answered the questions, we've given you some caffeine, we've given you some sugar that hopefully will take you through till 4 or just a little bit after, and then you can enjoy the weekend. Continue on about open access. Our next speaker is Matt Todd. Matt is a senior lecturer in organic chemistry, and he's also the boss of the Todd Research Group here at the University of Sydney, whose motto is actually to synthesise the right molecule in the right place at the right time. And I'm just hoping you could give the Latin translation. I'm only joking. Matt has also, like Alex, has also been a keen advocate of open access and open science, and early on in the repository life we had some discussions with Matt, and slowly now we've sort of come to fruition. Again, Matt, like Alex, were a bit thinkers ahead of their time, and we're now sort of catching up at a rate of knots to their wonderful advances. But today Matt's going to talk to us about the whole notion of open science. Thank you.
Thanks, Dan. It's good to be talking at an event like this. I like events like this which are focused on a specific thing rather than a general scientific theme, something which is more specific. It's a nice talk so far about the important aspect of open access publishing, and I guess I wanted to talk a little bit about a project that we're doing which is influencing more and more of the group now, which is something called open science, which is where everything is shared completely as it's happening, and for which open access publishing is necessary. Otherwise the whole thing's ridiculous. So you have to do everything in the open and collaborate with anybody in the world, so there are no borders at all, and therefore you publish in open access journals. So that's the idea. But I wanted to distinguish those two a little bit, and we got into it, into this idea from things that were happening in the early 2000s in areas of software design and things that were happening on the internet. And I was blown away by stuff that I was seeing, for example, in Wikipedia and Firefox and Linux. These products which were being developed, which were extremely high quality things, being developed by a sort of mass of individuals working in a sort of chaotic model. And I loved this idea, and I thought this is, given that Wikipedia was so good, I thought Wikipedia was good from day one, but I know a lot of people didn't. And now, of course, everyone uses it in secret at night when no one's looking. We all use it, and then we go and give lectures about how important textbooks are. But these are high-quality things. And of course, this is anathema to academia. Academia works, this is a well-known software development analogy of the cathedral versus the bazaar. And academia is a cathedral model where everyone works in a pyramid scheme. There's a boss, there's other people below them and other people below them, and it's closed, and everyone is highly trained, and it's very expensive. But you build something beautiful, and academia traditionally works along this model. In contrast, the bazaar model is more like the open source software model, or like Wikipedia, where anyone can show up, and it's a little bit chaotic. And you show up and you do something, but you don't really know who's in charge. But this thing emerges from this chaos, which can be extremely effective with a low overhead. So we were wondering if we could do science in this bottom way, rather than in the traditional way. And the reason, I'll come back to why we wanted to do that. There are some examples of many people working together on the internet in science already. So where anybody can collaborate with anybody to solve a problem. Perhaps from our point of view, the most successful is the Polymath blog, which is a problem in pure mathematics was solved by a bunch of mathematicians who got together on a wiki and worked together. Small number of people. Very, very successful project and a great idea. That's where the people who are taking part have high-quality inputs to offer. In contrast, there are other things like Galaxy Zoo and Foldit, which are beautiful projects and extremely successful in their own right, but where people come along and do quite simple tasks. In the case of Galaxy Zoo, the public are asked to classify galaxies by shape. And in Foldit, they're asked to play a computer game where they manipulate proteins as part of a game in real time and find minimum energy conformations of proteins. It turns out, this was published last year in Nature, and it turns out that humans beat the computers at this problem, which is why it was so important. And then many of the people who were the Hall of Famer scorers on Foldit had no experience of university biology at all. So lots of things there which involve people participating online for free. And this project, the Open Source Drug Discovery Project in India, has recently got going, and we're working with them on something I'll mention in a minute. So we had this problem, this is a bit of chemistry, we had this problem, we wanted to make this molecule and not this one. These are enantiomers, mirror images of each other. Molecules like this exist in nature, and thalidomide was one of these cases where people took a drug that was a one-to-one mixture of the two, and one is good for you and one is bad for you. In the case of our molecule, praziquantel, we wanted this one because it's effective, and didn't want this one because it was bad for you and very bitter. And this drug is given to underdeveloped countries on a huge scale. Hundreds of millions of people have the relevant disease that this drug treats, a disease called bilharzia, or schistosomiasis, a parasitic infection that you get if you swim in the wrong lakes in Africa. This drug is needed for a very low price, and the World Health Organization wanted this one and not this one. And this is generally a difficult problem in organic chemistry, to make one of these things rather than the other one. Symmetrical stuff in your life, like the pencil you're using or the Mac you're using, these symmetrical things are generally rather cheaper than unsymmetrical things like Rodin sculptures, which tend to be more expensive. So it's the same thing in chemistry. If you want something very asymmetric, which doesn't occur in nature, then it's usually more expensive. So we wanted this thing very inexpensively, and it was that price constraint which was the problem. We wouldn't be able to solve that problem on our own in the lab in any reasonable time frame. We had to have help from around the world. And so we decided to throw that open to the world. The idea is that, this is just a graphic that says that the idea is we wanted everyone to work together at the same time, right? Which means you have to release everything you're doing immediately. You can't wait and publish and then wait for someone to read it and then for them to respond. And with these arrows being months of delay for peer review and for grant review and rejection. So what you have to do is share all of your data. That's the first thing. It's not enough, but the first thing you have to do, and we did this on a drug repurposing project a couple of years ago, where you do a lot of work and you deposit the data for free on the internet, which was something called the Tropical Disease Initiative a couple of years ago. And that's good, but there's no active collaboration. Similarly, when Glaxo did this amazing deposition of malaria data a couple of years ago, actually last year, which I'll talk about again in a sec, they deposited the data for free, and that's good. And that's open access data, right? But that's open data, but it's not enough because there's no collaboration involved. There's not actually a to and fro of discourse which accelerates the process. So you have to deposit all the data you're generating, but then you have to do more. So we started a website called the Synaptic Leap, posted this problem in 2006, and then sort of sat back and expected the web to solve this for us. And that's nonsense. You can't do that. As everyone knows who's ever asked a question on the internet, people often don't respond because why would they? What's the incentive? We had a dribble of suggestions, but nothing major, until we were funded. So the key was we got funded by a linkage grant with the World Health Organization through their TDR branch, which is Tropical Disease Research. And we started to then have someone in the lab full time. And so rather than having a lab book made of paper, which Galileo would have used, we decided to put it online. So it was electronic, firstly, an electronic lab book describing all of the chemistry that we were doing. And additionally, it was online, so anyone can read it. And there's no login, there's no barrier. Well, there is a login on this, but you don't have to log in to read it. You can read it whatever you want, and you can comment on what's going on. And so every day, a new experiment goes up, depending on the productivity of the person. But it's all there. If you trip over something and spill it, you've got to say that online, right? So everything is there. All of the data you acquire have to be there so that people have the sense that they're really involved at the grassroots of the project, and there's something hidden. And so as a scientist, you then have to get outside of the lab and promote yourself to an extraordinary degree because people have to know that the project is there. So I gave talks that went on YouTube, and Nature picked us up, and this blog called In the Pipeline, which a lot of organic chemistry picked us up. And after each of these things, our traffic spiked. We suddenly got more suggestions from the right people, which was important. So you do have to promote sort of what's going on. And the end result was that we had this massive input from industry, which said that you're going about this problem all wrong. You should do this approach. To chemists, this will mean something. That we shouldn't be trying to make the molecule from scratch. We should be doing something very basic called a resolution, which would have been familiar to Louis Pasteur. That is a much more less academically interesting, right, but more like the disc-seed approach. And that was because we had this dribble of advice from people in industry who said, we know how to do this, right? We can help you with this. And so we came across a tough problem in this route that we had that we couldn't solve. I posted a request on LinkedIn, which is a website many of you may be familiar with. Because I was browsing internet. There's a room in LinkedIn with like 1,000 guys who do process chemistry, which is exactly what this is, how to do organic synthesis on a large scale. And so about 10 people replied, and some companies replied, including this one, and we sent them a gram of this material. They sorted both of our problems out for us, gave us hits on how to solve it, and then we took that lead result and optimized it over the course of about 6 months to a point where it's now sufficiently promising that the World Health Organization are looking to scale it up. So we found a solution which is on the top line here, which takes the existing thing and converts it to the thing we want with a process which is sufficiently promising that it's now being looked at on a kilogram scale and hopefully on a ton scale. At the same time as our open approach, so that there are, I don't know, 30 people contributed to this thing in various ways. The bottom one here is a solution that was generated by a company, a contract research organization who were being paid by WHO to look into the same thing without us knowing. So we were working in the open and depositing on the internet. These guys were working behind closed doors. And the solutions which arose were very similar, in fact, which was interesting. So the unusual thing about this project, I guess, was that it was open science, so everything was on the internet. But unlike the Polymath blog and other things like Wikipedia, where you're talking about text and code, we were actually talking about experimental lab-based science, which is a bit different because there's real molecules that you have to get involved with. So the model of what happened then was that you have an electronic lab notebook and you have data. You then so that's the raw feed of everything. And then you have other things which are discussion sites, which are this is a WordPress blog. A Drupal blog is a simple blogging platform. We had a wiki where we could assemble the paper. So we wrote the paper that was published on the previous slide. We wrote on a wiki site called Open Wetware. Until the point where we had to put in references, and I couldn't work out how to do that on a wiki, so we had to put it into Word at some point. But that was a technical limitation. And then it was published. There was a commentary in Nature Chemistry, and PLOS published the paper in PLOS, Neglected Tropical Diseases, which is the best place for it. And then, of course, now begins the process of post-publication peer review, where people then start chipping in after it's been published, which is the real value, I guess. If people didn't know about the project, they can now really see exactly a succinct summary of where we were at. And then once it's published formally in a peer-reviewed public, so 3 reviewers read this thing and said, okay. And now other bloggers start picking it up and saying, oh yeah, no, I like that, and what about doing this and stuff. So there's this dialogue that happens. And then you take those suggestions and you go back in the lab and start doing other things. That, to me, so A, this was an incredibly satisfying project because of that. B, that's what I think science is, right there. It's not working in a closed thing and occasionally releasing press releases of scientific papers to self-aggrandize. It's about this iterative process, which is a brutal, brutal form of peer review, where anybody at any point can say, nah, you've done it wrong, you made a mistake, which is just wonderful. So very exciting to see that, and also a feeling of acceleration of the science that we got. And I guess this isn't new, right, actually. It's just that we're trying to rediscover what science is. This isn't new at all. The Oxford English Dictionary was constructed by this process, by a process of crowdsourcing. If anyone's ever read The Professor and the Madman, this is how it was. So in any word in the Oxford English Dictionary, there are examples of typical usage and first usage. And the first usage cases were found by members of the public who were reading books and write on bits of paper, of course, writing in to the compilers of the dictionary about the fact that they'd found the first use of the word. And of course, if anyone was then reading a book before this publication date and came across the word collaborate, they would suddenly write in, I beat this by a few years. I found the first use, right? So there's a massive crowdsourcing project, incidentally, in which people were asked to do quite a lot. They were asked to read books and keep their eyes open for the existence of words. So it's not new at all, and the Oxford English Dictionary is a beautiful thing that was created from that process. The next thing that we're doing right now is to see if, so we were doing organic chemistry to resynthesize in a better form a known drug. So there's a discovery of a route there, but it's a known compound, which we were improving. The question is whether you can find a new drug where there's a much more complicated patent landscape. So a new compound which hasn't existed before. And we were just recently funded by the Medicines for Malaria venture, and we're going to find out next week, probably, about whether we've got a linkage grant on this to continue it, whether we can find a new compound for malaria using this kind of approach. So again, rather than having things happen behind closed doors, you have everything on the internet where you have a lab book. This one is currently being maintained by Paul, who's sitting at the back, where all the data are posted, and there's a discussion page where people can post links. We essentially are on all of these things so that people can interact with us in whichever way they feel comfortable with. We're not trying to build a website, we're trying to use existing things. And see whether we can go from known compounds, which were released by Glaxo in 2010, which are extremely good hits, and optimized to some compound, which we don't know what it is yet, in an open approach, and therefore try and get people to work with us on this. So anybody can come up to this project and begin to get involved, either advice or making molecules. That's the idea, and we're going to see if that works. And the laws behind this are as shown. So everything is shared, the data and the ideas are shared. Anyone can take part. There are no patents at any point because that's exclusive and would ruin the whole thing. This is about no flame wars. It's better to have public discussion. Every time I get an email about this project, my heart sinks. And I say, why can't you just ask me this in the public domain? What's the problem? Just post something on the website. That would be much better. And the important thing is we don't own this, right? We are starting it and we're leading it because Paul's in the lab and I'm thinking about it. and we have some money to do it, but we don't own this thing. So if we don't get funded, or if I fall under a bus on City Road, the project lives, right, because it's there. Everything is there. It's not buried in the lab book in the basement of chemistry. It's there, and anyone could just step right up and carry on. That, to me, is also what science is all about. These are the guys. So Murray is doing he's resuming the Praziquantel project. He's also at the back there, and Paul is doing the malaria project. So these are the guys, and Michael did all the initial work. So these are the guys who did all the work, and there's some funding guys there. Thanks.